So, hi everybody. Welcome back to the Astro Imaging channel. This is Alex, and I'm sitting here with Tolga and Eric and Terry and Molly and Bob. And Bob's going to be telling us some really interesting stuff a little bit later. I think we all know what the Hertzsprung-Russell diagram is. It's an attempt to show the life history of stars, and depending on what size the stars are, and that me.
Tolga, that's your other screen that's not muted.
Okay, let's get rid of that. Okay, sounds like we're good. We all know what the Hertzsprung-Russell diagram is. It's an attempt to show the life cycle of a star, and over time, stars change how their size and everything else like that, depending on how large they were to start with. And they go through different lifestyles. Well, it's possible for you to take deep space images of certain objects and kind of categorize all the stars in them and somehow or another come up with your own Hertzsprung-Russell diagram for, say, M44 or some other, a globular cluster or something like that. And it can be rather fun to do. And it's the kind of thing that we should do when we're, taking more than pretty pictures, when we're trying to add to the science of astronomy and things like that,
Science!
and also just for the challenge of it. So at any rate, I want to take you over. I want to share my screen for a little bit because I want to tell you a few things that are coming up. So let me click on the sharing screen and click over to here. And you should be looking at the Google Calendar. Um, Unfortunately, our website is a little bit messed up still. We've had some hacking with the website, and as a result, we're still under construction over there. We're trying to rebuild it, and we are working on that. So the only way to get to Google Calendar is to go to Google Calendar and stuff like that for right now. But at any rate, in December, we've only got one more event left. That's Tonight we've got Bob Vanderbei here, and then we're going to have, if I don't mess this up too badly, then we're going to have Tim Connolly come and visit with us next week. And Tim will be telling us about imaging in cold weather. And that's something like we really should know. We just spent the pre-show here talking about Molly's new mount again, and Molly and the weather and everything else like that. So
It's fun.
and then the week after that, happy holidays. We aren't going to be here. Oh, I should say Tolga's not going to be here next week either. And Tolga's the guy that actually makes all this stuff work. And so we hope everything will go fine because we've got some amateurs coming in to take over for Tolga. But the week after that, we're on holiday. And then the week after that, we're coming back with Bob Reeves. Bob Reeves is a really good lunar imager and stuff like that. And basically, our whole month is going to be filled, and we're pretty much filled all the way in through February. Warren Keller's coming, and a few other people are coming to visit with us. So we should have some good shows coming up for you. But tonight, we're going to have tonight Bob Vanderbei is coming to us. He's coming to us from um, uh, um, he's coming to us from Princeton University. And what does he do there? Well, he's a professor, and he's a professor in, let me get this back up here, operations, research, and financial engineering at Princeton. Now, you're saying, so what's about astronomy? Well, he also happens to work with the mechanical and aerospace engineering, mathematics, astrophysics, computer school, and a whole lot of other things at Princeton. I doubt Princeton could go on were it not for Bob being there to help him out. But at any rate, that's enough about Bob. Let's hear what Bob has to say. Bob, take it away.
Thank you. Thanks a lot for the really nice introduction. Yeah, I've done many different things over the course of my lifetime, but the thing I like the most, and I think this has been true pretty much all my life, is the astro stuff. And I was interested in astro when I was a kid, and it was the Apollo era, and that was a lot of fun. But I ended up doing other things with the early years of my life, and then about 20 years ago, I got reintroduced to astro stuff by one of my friends at the university, and started out just doing amateur stuff. I bought myself a Questar, started just taking it out in the backyard every night that was clear, which was basically every night back then, and then got into astrophotography a few years after that, and so this has been going on for about almost 20 years, and so tonight I'll talk about analyzing these astrophotographs and making Hertzsprung-Russell diagrams, and talk about some of the things that we can deduce from those diagrams. So let me go on to the next slide here. So here's a brief outline of what I'll do tonight. So I'll start out by showing you a little bit more details about the equipment that I have. And I have taken literally hundreds of, as probably many of you have also, hundreds of astrophotographs. And I have a web page with the whole gallery of all the pictures I've taken. But I'll just show a couple of my generic astro photos tonight, just to give you a sense of what you can do with my equipment. And then we'll zoom in, no pun intended, on Hertzsprung-Russell diagrams. And I'll do a brief introduction for those of you who either don't know it or don't remember about it sort of from a theoretical perspective. And then I'll show you how I was able to make HR diagrams from pictures that I've taken. And also then we'll transition into RR Lyrae stars, which are a component of of globular clusters. And also that's relevant for measuring distances to various things. So that's sort of an outline of what I want to talk about over the next hour. So let me start by showing you not my Questar telescope, but two other telescopes that I bought back in the year 2005, so 14 years ago. I bought a Ritchie-Chrétien from Ritchie-Chrétien Optical Systems, and I bought a Takahashi FSQ 104 refractor, and I've put them on this mount here. It's a Takahashi mount, and let's see. Let me show you the next picture here. I bought all these things in 2005. They arrived all these pieces that you're seeing in this picture over the course of about a month, including the little wheelie bar underneath that I can roll around, and the tripod and the mount and the two telescopes. And I set the whole thing up. Oh, and I also bought that, you see that little ramp into my garage? Because the wheels on that wheelie bar thing are too small to really go smoothly up that little lip into the garage. And so I bought that little metal ramp thing. And so I bought all this stuff, and I've set this up back in 2005, and I've never taken this telescope anywhere, these two telescopes, anywhere other than my driveway, or a little bit up and down the sidewalk occasionally when I'm trying to avoid some trees. And in fact, here's a picture of a typical setup. That took this picture many years ago, but it doesn't look too different today, other than that the trees along the side of my driveway, which are small in this picture, have now gotten a bit bigger, and that's become a bit of a problem. But that's my setup. I just work on my driveway. And here's a picture, another picture of me on my driveway while I was taking some pictures. And so that's my setup. And just let me show you just a few pictures I've taken with that equipment. So here we have the Crescent Nebula. This is one of my more recent pictures, actually, with my Starlight Express camera attached to the telescope. And I've taken pictures of the Crab Nebula. In fact, by the way, I've taken more than one picture of the Crab Nebula. Here's one I took just last year. This one I took 12 years ago. Notice how the Crab Nebula is getting a little bigger. I actually was able to use these two pictures of the Crab Nebula, and knowing exactly how many days apart they were, and assuming that this explosion that we're seeing from a supernova event is moving out sort of at a linear pace from the explosion, that if I just go analyze those two pictures and ask myself, how long ago did that explosion take place? I get the right answer to within 10 years. The right answer, of course, as probably many or all of you know, is the year 1054 AD is when that supernova happened, and I get 1040 something AD. I forget the exact number, I didn't look it up. But just from those two pictures of the Crab Nebula, so that's one of the things I'm very excited about is how we can actually do science just on our driveway. Here's another picture I like a lot. I like this one because it's named after me. It's called the Dumbbell Nebula. That's a joke. M27. It's also just beautiful, and I just love taking pictures of M27. I've also taken several pictures of it over the years. Okay, so that's, oh no, I was going to show you a few more pictures that I've taken. This is a picture of an open cluster called Messier, I believe it's 39. And so that's a fun one. And here's a picture of the, what is it called? The Beehive Nebula, M44. And so I'm going to show you Hertzsprung-Russell diagrams of these open clusters as we go further along. And here's the best picture I've ever taken of the globular cluster M13. The frame, the images here had a full width half max of about 1 arc second. And for me here in New Jersey, taking pictures from my driveway, usually a good night is about 2 arc seconds, or sometimes 1.6. And I'm really happy if it's 1.5. I was shocked that the full width half max here was 1.0 arc seconds. This is multiple frames. One of the frames was 0.96 arc seconds, and the stacking of these images was only, I think, 1.1 arc seconds. So, I mean, this was just amazing. And so anyway, that's also going to be part of our HR diagram story as we move forward here. And every 10 minutes or so, I'll pause here and ask if there's any questions. There might not be any questions yet because I haven't really said anything of significance, but should I pause here and ask if anybody has any questions for a second?
Somebody on YouTube was asking what kind of mount do you have?
Oh, it's a Takahashi, what's it called? SXV. Isn't that what it's called? Yeah. It's a Takahashi mount. It's not an astrophysics mount.
What size is your RC, Robert?
It's 10-inch.
Ah, fantastic.
Yeah. It's a 10-inch f9 scope. And the FSQ refractor is, what is that? It's f4, I think, isn't it? I forget.
It's a F5 106.
It's an f5? Okay. Yeah, and I said 104 before. I meant to say 106.
Molly, it's the same as yours, the blue one.
Yes, I love it. It's the best.
Yep, it's pretty awesome. They're both pretty. Both of those telescopes are pretty awesome. Any other questions, or shall I go forward?
Go ahead.
No, we're all set, Bob. Just continue on, please.
Okay. So probably everybody on this system here knows what an HR diagram is, but let me just review it briefly anyway. So here's a picture I just grabbed off the internet. An HR diagram is a plot. Horizontally, we're plotting the temperature of the star, which is also related to the color of the star. So we can call it a color diagram or a temperature diagram. And so hot stars are blue and cooler stars, not cold, cooler stars are red. And for anybody who finds that counterintuitive, just if you have a gas stove, when the flame is really hot, it's a blue flame. And if your flame's almost going out, you might see it turning red. And so hot is blue and cooler is red, but they're flames no matter what. We're talking 30,000 Kelvin for blue and 3,000 Kelvin for red. So that's the horizontal axis, and the vertical axis is the brightness of the star. And this isn't the brightness of how we see it. This is called the absolute brightness. If we could put all the stars the same distance away from us, and this would be a plot of their brightness. So on this chart, it's calling it luminosity. Other charts call it absolute magnitude, and the units are different, but it's the same idea. And I will mostly be talking in terms of absolute magnitude. And the definition of absolute magnitude is the magnitude of that star if we were able to view it from a distance of 10 parsecs. So some stars are closer to us and they're brighter because of their closeness, and other stars are further away and they're dimmer because of their farness. And this is a complicating factor in everything we're going to talk about tonight, is the fact that how bright a star appears isn't the same thing as how bright it would appear if it were exactly 10 parsecs away from us. But if we can figure out how to make that adjustment, and if we know how far a star is away, we can adjust it because there's something called the inverse square law. And if it's twice as far away, it's 1/4 as bright. And we can convert that 1/4 into magnitudes. There's a simple little equation for that. But anyway, so if we know how far away these things are, if we could measure it by measuring their parallax or other ways of measuring these things, then we can correct the visual brightness, the apparent magnitude, and correct it and replace it with an absolute magnitude. And then we can make a plot of the stars and we get a chart that looks like this. And the most important thing, or the most interesting thing, or the most popular thing of this chart is this diagonal that goes from the upper left to the lower right, which, as is marked on the chart, is called the main sequence. Most stars spend most of their billions of years of existence on the main sequence. So when they're first formed, they're on the main sequence, but as they age and the dynamics of what's happening in the nuclear reaction, the core of the star changes as it gets older, the hydrogen gets burnt up, or whatever you want to call it, and it starts fusing helium and other things, carbon and stuff eventually. The dynamics inside the star changes and it leaves the main sequence and it moves up to the right into what's called either the giant or the supergiant zone. But it's up there a much shorter time in its existence. And so it moves up that way, and it's there not for many billions of years. It's there for a long time. We're talking millions and maybe even a billion. I don't remember the exact numbers, but not tens of billions. Actually, it's probably not even 1 billion. But it moves up into the red giants and the red supergiants for a while. And then as it gets even older, then it migrates off to the left and then down below into this white dwarf region. And so there's a whole dynamic, sort of stellar evolution is, I guess, the technical term for what I'm sort of describing here. And this is what we want to talk in a little bit more detail about. And so let me go to the next slide. I wasn't sure if I should show this one, so let me just be brief here. This is just showing you some of the terminology in the astral world. The colors of the stars in the early days, they used letters O, B, A, F, G, K, M, L, T to categorize the different star temperatures or colors. And the absolute magnitudes also have different names. You've got the white dwarfs, which I was showing you on the previous slide. You've got the main sequence, which is also shown here. And then you got the giants and the bright giants and the supergiants and the hypergiants. And you got the different classes, 1A, 1B, 2, 3, and so on and so forth. This is just showing you how the standard notation, standard terminology in the astral world is related to the color and the brightness. But let's go back to the Hertzsprung-Russell diagram kind of picture. So here's the same, roughly the same picture, just with a little bit less details shown in it. And let's see, what do we have? Oh, yes, and I wanted to show you a video, if you don't mind. I think I have to escape here. I want to show you this video here on the Hubble Space Telescope website. Let me click on this, go full screen, advance us to about 10 or 11 seconds into it. This is the stars in a nearby galaxy. That's how they look today in a color magnitude diagram. But this animation is going to show you how they looked 1 billion years after the galaxy was born. And it's showing a dynamic, this is a simulation that was made by somebody, but showing how the stars evolve off the main sequence. And the stars that are up near the top left of the main sequence, they evolve off first because they're brighter, they're hotter, they're burning faster, they have a shorter life. And so that's just an animation of the dynamics. But of course, what I'm doing with the HR diagrams is not something over billions of years. It's just maybe something over 5 or 10 years. And so we're not going to see too much in terms of the dynamics, but I did want to show that to you. But anyway, so this stellar evolution stuff is really cool, and that's what I want to get to. And so before I show you how I make the HR diagrams and what the HR diagrams can tell us, are there any more questions?
Bob, I think we're waiting for you to move on. There's a couple of commentaries, but I think the questions will be answered.
Okay.
We'll get into your presentation more.
Okay, I'll keep going. Okay, so here's a picture, a diagram that I made just a few weeks ago. This is with what's called Gaia data. Gaia is a European Space Agency, ESA, a space telescope that's been up for, what has it been up for, like five years, I think? Something like that, taking pictures of stars in all directions, and it just is accumulating the best data. And it's not just getting brightness and color, it's also measuring parallax. And so the Gaia mission has measured the distance with rather good accuracy to thousands of stars. In fact, in this picture, as I recall, I downloaded 70,000 stars. This is all of the Gaia stars that are within 100 parsecs of our Earth here, and I made it, and I made a color. I made a HR diagram because the Gaia data is actually pretty easy. I mean, all you have to do, there it is at the top here, Gaia. Just type Gaia, and of course, there's lots of things that are called Gaia, so you could put the word astro after it, or you could put DR2, data release 2, and then they'll know you're searching for the Gaia data, and it'll take you to the website where you just fill out a form and you can download. Most people don't download the entire night sky like I did. Most people download a section around a globular cluster or an open cluster or something else they're interested in. But anyway, it's very easy. You can download the data in various formats. I downloaded it as a comma separated values CSV file. And in this file, it gives me the blue minus B minus V, blue minus visual color index, and it gives me the magnitude, and it gives both absolute magnitude and relative magnitude and distance, because it's measuring the distance with the parallax. And so I had all the data, and I just wrote a little Python script to just to make a plot of the color versus the absolute magnitude. And what we're seeing is the vast majority of the stars that are within 100 parsecs of us are on the main sequence. That's what we're seeing here, this diagonal from the upper left to the lower right. We're seeing some stars that are evolving off it near the upper left. And we're also seeing some of the white dwarfs, which I guess I'm plotting a little bit bluer than I should, down below. And I only made this a few weeks ago, and it's quite sharp, but there's a few things I don't understand, which I'd like to understand, and maybe some of the people listening here might be able to answer my questions. Like, for instance, why does it seem like there are little 2 segments here? Is that something weird in the Gaia data? I mean, I don't think I plotted things wrong, so I'm a little bit puzzled why there's 2 things there. And I'm similarly puzzled why it looks like there's 2 strips here as well. That's a question I haven't figured out the answer to yet, and I hope to think about it and try to learn from the Gaia people themselves over the course of the next few weeks. So that's perhaps my best HR diagram using not my pictures, but the Gaia data. And if we go back in time a little bit, before the Gaia mission, there was another mission also by ESA called Hipparcos. And here's an HR diagram I made using Hipparcos data of all stars that Hipparcos had good data on within 100 parsecs. And you can see it's a lot fewer stars than Gaia. And that's because Hipparcos, I think, was a satellite launched in the, I forget, the mid-1990s, if I remember correctly, something like that. So like 20 years earlier than the Gaia one. And you know, CCD cameras in the mid-1990s were a much newer thing, and the whole technology was much more primitive back then. And as you can see from these two pictures, the Gaia HR diagram is dramatically better than the Hipparcos one. But nonetheless, the Hipparcos one does show quite clearly there's a main sequence, and there's these red giants up in the red zone, and there's some blue white dwarf stuff down in the lower left. And this is what an HR diagram is supposed to look like. This is what Hertzsprung and Russell first realized about 110 years ago, that there was some very important, interesting stuff going on here. And I'd like to go back actually a few pages here and go back to my pictures I was showing you. I mean, so as we look here, a very fundamental question that I would have looking at this picture is, that's an open cluster. Messier thought it was a comet. Okay, so he was confused, or maybe he was just liked this group of stars. But anyway, this is an open cluster. But the question is it just random stars that happen to appear as a clump? You know, that can happen randomly. But if they just happen randomly, they wouldn't necessarily be the same distance from us. They could just be, apparently, as we look at them in the sky, they look like a clump. But are they a real clump? Are they also the same distance? And that, as you look at this, I don't know. Can we figure that out? From the picture that I'm showing you here, can we figure out if this is a clump of stars in three-dimensional space, you know, all out at the same distance, or not? And that's the kind of thing that I think is really cool, that we can answer that question using pictures that we've taken with our telescopes and a little bit of coding. So that's what this is about. Okay, so I've shown you these two. Let me move on here. Oh yeah, so here's the open cluster, M44, as the A44, Beehive cluster. I've rotated this 90 degrees just to make it look like it's in landscape, not portrait mode. So north is to the left here, as probably you all recognize, but that doesn't matter. But anyway, this is a cluster of stars. Same question here. Are they all part of a cluster that's the same distance from us, or are they kind of all random? It's not clear a priori. There's the HR diagram that I made of the Beehive cluster. And you can see there's a main sequence kind of thing going on here. But now the important thing is, look on the left side here, where I labeled the vertical axis, brightness. It's not labeled absolute magnitude because I don't know how far away these stars are. This is just a picture I took. This is apparent magnitude. This is how bright they appear to us here on Earth. Now, if they were all the same distance away, the apparent magnitude would be not exactly the same as the absolute magnitude, but they'd all be off by the same constant. You would just shift the picture appropriately depending on how far away it is if they were all the same distance. If all those stars were 10 parsecs away, then the apparent magnitude and the absolute magnitude would be the same. If all those stars were 100 parsecs away instead of 10 parsecs away, that's 10 times further, that's 100 times dimmer. We can convert 100 times dimmer into a change in magnitudes. What is that, 5 magnitudes, I think? But anyway, the picture would look the same. It's just the numbers on the left, on the vertical axis, would be different. So the fact that we're seeing a band here of stars, a main sequence kind of band, is telling us that maybe not all the stars in that picture are part of a clump, but a lot of them are. It looks like about half of them are on this main sequence band. And the other stars that are sort of random below it, they're probably just other stars further away. And there's the bright stars up above, well, they might be part of the same group because, as we've seen, a smaller fraction of stars can be in the red giant branch. And so those might be red giants from the same cluster, or they just might be bright stars that are actually closer to us. And I don't know the answer to that relative to this particular HR diagram, but this HR diagram does convincingly prove that we're looking at a cluster of stars that are the same distance from us, together with some background stars and maybe some foreground stars. But the majority of the stars in the Beehive are a clump of stars that are all clumped together. So I think that's really awesome that you can deduce this just from a picture that you can take from your driveway. And for fun, back when I first made this picture from my data, I then went onto the internet and downloaded some data about the Beehive cluster. And I did this HR diagram quite a few years ago. And back in those days, I used Vizier data. And you get a picture that's very similar to mine. There you go. My picture, the picture with their data. And that was pretty interesting. So I got all excited about these things. And of course, now let's talk about the globular cluster M13. This is, again, my best picture. This is a globular cluster. I think everybody here on this session knows that a globular cluster is a three-dimensional glob of stuff. It wouldn't make any sense for this to be visually a glob, but radially, some of those stars in the glob are way, way closer, and some of them are way, way farther. Then it would be like this cylinder that's pointing at us, and that doesn't make any sense. And so it seems just common sense that as you look at this globular cluster, you're going to deduce that all the stars in the globular cluster are roughly the same distance from us. I mean, of course, the ones that are a little bit in the front of, the ones that are in the front of the globular cluster are a little bit closer, but the scale of things here is pretty small. The angular width of this thing is what, like, I don't know, 5 or 10 arc minutes or something like that. And when you can translate that into how much of a percentage difference in the depth would there be if it's the same kind of thing, and it's a pretty small percentage. We have to convert that to radians, and I could do this mental calculation if anybody wants, but anyway, it's a small, the close ones are only a little bit closer than the further ones in this cluster, and so we don't need to know the absolute magnitude of these stars. The relative magnitude is guaranteed to be good, and so I made an HR diagram of this using this data. And here it is. Here I'm going to go. There's the HR diagram of M13. And I think, as you're all probably saying to yourselves, well, that doesn't look right. It looks cool and it looks impressive, but where's the main sequence? And this is something that was discovered, I don't know, about 100 years ago, that the globular clusters don't look like our main sequence. And that's because, first of all, they're far away. Globular clusters are sort of on the periphery of our Milky Way galaxy, and therefore they're further away than these open clusters. And so if I'm taking pictures down to magnitude 18, that's still pretty bright in an absolute sense. If I could actually get absolute magnitudes of this globular cluster, those, even at the bottom of this picture, those are still bright stars. This is just the upper tip of the HR diagram that I was showing you before. And as we saw in the animation, the upper tip tends to burn off quicker. The stars peel off quicker because the hot blue stars age quickly and then become these red giants. And that's what we're seeing here. And this is the way that astronomers figured out many, many years ago that globular clusters are actually quite old. They were formed a long time ago, and they're very old and mature balls or globs of stars. And the proof that they're old is the fact that these stars, most of them, or many of them, maybe that's not most of them, but many of them are already trailing off. They're already in this end game part of their of their existence. But if we could go lower down, if I could go to magnitude 20 or magnitude 21, way down, if I could go further down, then I would see the main sequence, and it would go off down and to the right rather than straight down like it looks like it's going to do in this picture here. And so I've wanted for many years to take longer exposures of M13 and hopefully be able to image down to magnitude 20 something. But as all of you who've taken astrophotos know, we're talking pretty dim here. But this is only a 26-minute exposure, this picture of M13. This is RGB and luminance. I did the R, G, and B for 6 minutes each. 6 times 3 is 18. I did luminance for 8 minutes, a total of 26 minutes. And these were multiple images, 20 seconds each, to make sure that none of the bright stars saturated the pixels on the camera. And so so there are lots of pictures here, but it's only 26 minutes of total exposure time. And I've wanted to go back and take multiple hour exposures to try to see if I could push this down further, but I still haven't done that. But Tolga, who's part of our group here tonight, did that last spring. He took, what did you say, Tolga, like 15 hours or something? I forget the number you said. Many hours.
Yeah, something 13 or 15.
Yeah, 13, whatever. Yeah, many hours. Way more than a half hour. I took about a half hour. You took 5 hours, would be 10 times. You took about 20 times of the length exposure, and even more than 20 times, 20 to 30 times more long exposure to get this picture. And by the way, this picture looks quite different from this picture. So different that when I first looked at it, I'm like, did Tolga really take a picture of M13? Because I love M13 and I've kind of memorized where the stars are because I'm kind of a nerd that way. But eventually I realized my favorite 3 stars in M13 are the stars right here. I hope everybody can see my mouse. That little triangle there in my picture is up here. So that's kind of in the bright core in Tolga's picture, where it's getting out in the periphery in my picture. And that's the difference between a 13-hour exposure and a 30-minute exposure. And so Tolga got way deeper in the exposure times. And so he sent me the FITS files last spring, and I made an HR diagram from this data, and here it comes. I'm going to hit the arrow key. That is awesome. And it was an APOD. Look at how deep he went. My thing was starting to fall apart around 18th magnitude. He's down to like 21 magnitude, 3 magnitudes further down. I mean, that's just, and it's nice and sharp down here, and it's amazing. And so, now there's a few other things to say about both his picture and my picture. One of these is, most of these other things over here, this is probably just other stars that are not in the globular cluster. You point your telescope in any direction in space and there's stars in your picture. These are probably just other stars, and most of this is just other stars. And maybe even these bright things up here are just other stars having nothing to do with M13. But the fact that there's a structure here, this structure would only exist if there's some correlation between all the stars, and that correlation is they're all in the globular cluster. And also, by the way, this part over here is part of the globular cluster as well. And I'll say a little bit more about the dynamics of globular clusters in coming slides. But yeah, the structure that you're seeing here is because the globular cluster is all basically the same distance away, and we're seeing the stellar evolution being exhibited to us in this cluster. So just for fun and inspired by Tolga's picture, I went and grabbed the Hubble Space Telescope picture of M13. Unfortunately, the Hubble Space Telescope's detector sensor isn't that big for taking pictures of rather large things. So here's the best I could get for M13 from Hubble, which isn't the whole globular cluster, but it's a chunk of it. And when you're making HR diagrams, it doesn't matter if you're just taking the upper left part of the globular cluster, because the lower right and the upper right and blah, 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 they're all going to be similar. And it's all going to be just be more stars, but the picture should look the same. And so here's the picture I get using this data from Hubble. And it looks quite similar to Tolga. In fact, actually, to tell you the truth, Tolga's looks better. But they look very similar. Go back to Tolga's, go back here. Oh, I wanted to mention one other thing about Tolga's pictures, and I could be wrong about this, but the fact that this part here seems to be pointing upward, I think, and I could be wrong, and Tolga could correct me, my suspicion is that these are like, what, the 15 brightest stars in the picture, well, maybe together with these, but, and I'm guessing maybe the red images were getting close to saturation of the pixels, and they might have, once you saturate a pixel, it doesn't collect any more photons. And so I have a feeling that that's what was happening, and that maybe this was supposed to just be continuing off to the right, but he might have been almost saturating his camera on those pixels for those few stars. And the Hubble one doesn't seem to have that behavior, nor did my picture of M13, my diagram for M13 either. Okay, let's take a few seconds break here. Any questions?
Well, I think everyone is interested in exactly how you go from the images or the FITS files to the HR diagram. There's been some questions over there. And I had a question that the Hubble telescope doesn't actually have RGB filters in it. So you must have assigned certain filters.
I did.
The red.
I don't remember off the top of my head what I did. But yes, it has multiple wavelength bands. And so, if you want the color index to match numerically to somebody else's picture exactly, then you need to use the same type of filter. But we don't, I don't really care that whether they match them numerically exactly correctly. And so I wouldn't mind if it's infrared and ultraviolet or whatever wave bands, as long as you have different wave bands. You can say this is the redder one and this is the bluer one. Then we can look at the luminosities in those two wave bands and say what color those stars are. So I wrote code to do this, and there's I didn't think it would I thought it'd be too nerdy to actually show code, although I have the code on my computer here, and if that's what everybody wants, I could dig up some code, but there are going to be links.
If you could show kind of the general mechanics, not the code, but how you get from FITS data and not operate the code, but what you use in order to get the diagrams and assign the colors to the diagrams.
I'm not quite sure what you're asking me. If you don't want to see the code, but you want to understand what I do?
Sure.
Okay, so I mean, I'll just, for example, I'll just take the red and the blue, the stacked image. Make sure a big part of all this is making sure you don't saturate any of the pixels. As I was just mentioning with Tolga, I think that those top pixels got maybe a little bit saturated. So that's why I always take short exposures when I'm taking pictures of globular clusters and open clusters, because I don't want those bright stars to be saturated. So that's one of the most important things. But so anyway, you get all these FITS files, assemble them, and I assemble them in IEEE floating point. So you can do this in all the various software packages for stacking images. I'm still using MaximDL because that was I think the only thing that was out there when I started almost 20 years ago. And now there are other packages which are very popular, which I haven't migrated to, and I'm not sure that I need to. But anyway, in all these different packages for aligning and stacking images, I mean, the most important thing is to do that and do it and then save these things out, not as JPEGs or not as PNGs, but save them out in well, you can save them out as FITS files in IEEE floating point format, so that you have the huge spectrum of brightnesses that go from several orders of magnitude. So that's the first and most important thing. So assuming that you have that, and so maybe you have a stacked luminance frame, a stacked R, a stacked G, and a stacked B. I could make an HR diagram just from the R and the B, but if you also have the luminance, that would give me maybe a better signal to noise ratio in measuring the brightness. I could just add the R and the B together and call that brightness. But anyway, I wrote code that automatically looks for stars in the picture. And that's the most sophisticated part of the code. Now, I think, I haven't actually done this in recent times, but I think some of these packages, IPAP and MaximDL and the various other Astro software will find stars and make charts, not charts, but make text files of data from them. But and maybe I should have refreshed my memory on those things before tonight's presentation. But being a nerdy person, I haven't done it that way. I've just loaded the FITS file into either MATLAB or Python. Originally, I did it all in MATLAB, and more recently, I've been doing it in Python. But they're very similar. And it's just a one-line thing. The actual syntax of that one line is different in these different languages, but it's just basically read this file, and now within these languages, I have the file and they're image files, and so I have pixels, and so I wrote code, and this was the part that I thought was the most fun personally, was to write code that tries to identify the stars in the file, in the image. And so I look for every pixel that's a local maximum. If the pixel above it, below it, to the left of it, to the right of it has a smaller luminance, I'm like, that might be a star. Now that's a little bit too simple, and so I did something a little bit more complicated than that. But that's sort of the basic idea. Is I looked at each pixel and looked to see, does it look like I'm sitting on the top of a hump of a point spread function of a star, and so that's the first thing the code does, and then it adds up the brightnesses of those nearby pixels and calls that how bright the star is. And it does the same thing in the red and the blue, and then it takes the difference of those, and that's the color, is the difference between the red and the blue brightness, luminosity, flux, whatever you want to call it. And so I just wrote my own code to do this, and I apologize for the fact that there probably is some code. I don't think there's code out there that will make an HR diagram, but I do think MaximDL and these other packages will do some of the work that I did myself of extracting the stars and telling you their flux and their color. But I apologize that I didn't actually think to do that before tonight's talk. So is that enough? Shall I go on?
Sure, that's great. Thanks.
Okay. So here is a picture that I didn't make from seds.org of M5. M5 is one of the more interesting globular clusters in terms of HR diagrams, and that's why it's a popular one. And I've made an HR diagram of my own M5 picture, but I like M13 better. But anyway, here's a picture that, astronomers understand how this looks. And this looks pretty much like Tolga's picture for M13. At the bottom into the very faint region, you've got the main sequence, which is going from the northwest to the southeast. But up toward the brighter stars here, you've got this branch off to the right. This is the red giant and supergiant regions, as is marked in this picture here. But then as the stars evolve, they go up into the red giant region up here, and then as they get old, they actually come back down this way and come over here, and then go down to what's called the horizontal branch. And I don't know why this person who made this picture colored this pink. I would have colored it blue, and I would have colored these red, but whatever. But this is the horizontal branch, and the stars, the evolution of the stars is that they go along here, and then in the horizontal branch, and then down this way. And as the stars get old, that's what happens. But the interesting thing here is that the stars here are called RR Lyrae variables. And they're also especially interesting. And that's what I want to talk about next. I don't actually know why I'm showing you this. Here's an HR diagram for M13 that I made many years ago with Vizier data, which looks too good to be true, but I don't know. I haven't refreshed my memory as to why the data here looks so unbelievably perfect. But anyway, let's go on. Oh, this is the reason I was showing this picture. Yes, so this is just to illustrate the evolution of the stars. They're for billions of years, they sit on the main sequence, but eventually they migrate up this way, and then they come down here, our Lyrae horizontal branch and down, like I was showing on the previous slide. Okay, now, I'm interested in the RR Lyraes, and let me get to that in just a minute. Here's the globular cluster M15, not M13. M15 and M5 are the two most interesting globular clusters in the world of RR Lyrae stars. M13 does not have very many RR Lyrae stars. And the RR Lyrae stars are the key thing that I want to spend the rest of this hour talking about, so maybe last 15 minutes here. And so, or 10 minutes. Here's globular cluster M15 taken with my Ritchie-Chrétien telescope on my driveway. And here is the HR diagram I made of M15. And as you can see, there's the horizontal branch, and our Lyrae stars tend to be in here. And if we go forward, I have even more to show you. Here is a picture of M15 that I made, sorry, not a picture, HR diagram that I made using two different pictures of M15 that I took. I took both of these pictures, I forget, like a year apart or something, it doesn't really matter, not within 5 minutes of each other. I took two pictures of M15 months or maybe years apart with the exact same telescope, the exact same camera. Everything was the same except for it was a different time. And I modified my HR diagram software to not just read in one set of data, but two sets of data, match up the stars, and then ask, oh, did the luminosity change very much in these two pictures? Now, of course, they all change a little bit, but most of the stars don't change a lot, but some of them change significantly. And so I set some threshold in my software. If it changes by more than this ratio, then we're going to call this a variable star, and I'm going to plot its brightness and its color twice on this plot. Like here's one where on one of the pictures it was over here on the left, and the other picture of M15, that same star, and the plot is way down here, down and to the right of where it was. So all these little line segments that you see are plotting the same star two different ways. All the other plots, all the other points here where the difference was too small, I just aggregated the data. And so you're just seeing the central brightness and the central color because it was just 2 points that were very close together in the data. So here I'm highlighting the stars where there was a significant change between the brightness and the color in the stars. And most of those are here. I mean, there was something going on up here, don't know what that is. There's a couple down here and a couple way down here. These are quite possibly just, well, they could be Mira variable stars if they're red. It's not clear. This could be a star that's not part of the cluster. In fact, I think it is a star that's not part of the cluster, given it's part of something up here. So I'm guessing this is probably a Mira variable star that's actually closer to us than the globular cluster. But there's, again, something systematic going on. And the systematic thing that we're seeing here are the RR Lyrae stars. And the interesting, why are they called RR Lyrae stars? It's because there's a star in the constellation Lyra called RR Lyrae, and that's this star right here. I took this picture with the same equipment. I took this picture. In fact, I took 2 pictures of this on different, I think exactly one night apart, and I can show you. Here it is, just one night apart. I don't know if it's easy to see, but the bright star, RR Lyrae in the center here, the brightness varies a little bit, and it's slightly blue, as we know.
That's extremely cool.
Yeah, and the other stars aren't changing at all. I mean, this is just so exciting. So, and I don't even know, is this the minimum? Is this the maximum? No, this was just 2 random pictures I took on 2 nights. And so the maximum brightness might be significantly brighter than what we're seeing here, and the minimum might be significantly dimmer. I actually don't know, but we're seeing a difference, and that's what's cool here. And by the way, it's known that that this star, RR Lyrae, is 258 parsecs away from us. That's been measured. So we can take that as something known, which is going to be relevant in the things I'm going to show you in the following slides here. Any questions about what I've said so far about RR Lyrae, or shall I go ahead?
No, why don't you go ahead, Bob?
Okay. All right. So here's a really fun thing I did. I took those 2 pictures of RR Lyrae, and I took my pictures of my picture of M13, and I stacked RR Lyrae onto my picture of M13. I just put it over in the corner of the FITS file. And when I did that stacking, I made sure I carefully adjusted for exposure times. As I said before, my pictures of M13 here were all 20-second exposures. I think I used shorter exposures for our Lyrae, and because it's a brighter star. And so I had to make sure when I added these 2 FITS files together that I appropriately compensated for the difference in exposure time. So these kinds of things you have to think about it carefully and do it carefully, but I did. And here is an HR diagram with from both RR Lyrae stars are there, so we're seeing the jump there. And M13 doesn't really have many RR Lyraes, but we know that if it did, or if it does, they're basically on this horizontal branch. This is not 2 different pictures of M13 taken 2 different times, so I can't really show you the little line segments like I was showing you with M15, but this is where the RR Lyraes should be in this picture from what we've already seen. So in this picture, they'd be about magnitude 14, but RR Lyrae itself is about magnitude 7.5 or something like that. And so actually this is more like 14.5. So I estimated that the difference in brightness between the actual RR Lyrae star itself and the RR Lyrae type stars in M13 have a difference in brightness of about 7 magnitudes, which I'm explaining down here at the bottom of this slide what I did with that. So RR Lyrae is 7 magnitudes brighter than the RR Lyrae stars in M13. We can convert that 7 magnitudes into a flux. And here the formula is down here on the lower left here. Magnitude 7, we have to divide that by 2.5. That's then the power of 10. And then we have to take the square root to get the difference in the distance. It's that the square roots from the inverse square law, and the power of 10 and the 2.5 are converting magnitude into flux. Anyway, it's just a simple calculation. Put the difference in the magnitude into this little formula here, do this calculation, and you'll get a number. With 7, we get 25. This is telling us that just using this data here, that I would guess that M13 is about 25 times further away from us than our Lyrae. And we know that our Lyrae, well, I said it before on the previous slide, was, what did I say, 200 and some parsecs? Translate that to light years. Our Lyrae is 860 light years away. This is something that we're taking as known. I didn't actually I didn't find this myself, but you Google it. Our Lyrae, the star itself, is 860 light years away. M13, my estimate based on this data, is that it's 25 times further away. 25 times 860 is 21,500 light years. My estimate of the distance to M13, based on these pictures I took from my driveway, is that M13 is 21,500 light years away. And this was really exciting to me because when you Google it, Wikipedia page for M13, it tells you that M13 is about 22,200 light years away. So I'm right to within like less than 10%. That's just amazing, just from these pictures from my driveway. So I was very excited about that. And similarly, I compared M3 to M13. Here's a picture of M3 that I also did with the same telescope on my driveway, the same camera. It's not as pretty as my M13, and it's not as sharp because the seeing wasn't as good, but I know my exposure times. I can compute the fluxes carefully and compare them to M13. And so here's M13 again, and I actually made an HR diagram that combines the data from both of these pictures, adjusting for exposure times appropriately. And here is the two HR diagrams layered on top of each other. Now in the data, I actually know which pixels go with which, but you can see, one of them looks like it's brighter than the other one. You can see the branch up here is higher than the branch here. And we can estimate this difference here. What is it? Just visually, I'm guessing that's like a little bit more than 1 magnitude or something. And you can see the horizontal branch of the one, the horizontal branch of the other. It looks like, I don't know, about 1 magnitude. I actually wrote code to sort of do this estimation in a more statistical way than what I'm just saying here visually. And I think I have that summarized on the next slide. Here it is. So my code my Python code, there's a link to the Python code right here. You can all click on it later. My code estimates the difference in magnitude as 0.7 magnitudes. Converting 0.7 magnitudes into flux gives me this flux. Take the square root of the flux. That's the relative distance factor. And if we relate then M3 to M13, M13 is the brighter one, so M13 is the closer one. And we know that M13 is about 6.8 kiloparsecs. Again, I'm going back from light years down to parsecs stuff. 6.8, 10.4. These are the known things. When you go to Wikipedia for these two globular clusters, those are known numbers. You take the ratio of those two numbers, you get 1.5. And I got basically roughly 1.4 just from those two things. So that's pretty amazing. And by the way, these are links also. So those of you who go to the slides for the talk later, and there's a link to the slides at the very first slide. There's a link. You can download these two FITS files if you want. I'm pretty sure these links still work, although I haven't clicked on them recently. If they don't, I'll fix them later. And you can click here to see the Python code. And I did click on this, and this does work. And so you can download this Python code and run this Python code with these two data files and produce a picture that looks like that. So that's all I had to say. Thank you, everybody. And are there any final questions?
Bob, I assume Tolga is going to post your presentation so people could go through and click on some of those links.
No, they are already on the bottom where the details about the video, under the video, everything is down there already.
Okay, there is a lot of discussion about how this is done. Is there any reading that you'd recommend, Bob, for people who might want to generate their own HR diagrams?
Ooh. I mean, I just Google things all the time. I used to read books.
Bob, could you hang on for a minute and
Sure.
think about that question? Maybe I want to click on my screen. I should be sharing my screen, aren't I? Oh, where did I go? Oh, this is where I want to be. I'm sharing my screen, aren't I, Tolga? And
Yeah,
at
you're-
the
Yes, you
bottom, at the bottom of the presentation, you'll notice a number of links. Okay. And that's where we're talking about. If you want to find this stuff, you can go down to those links and you can find that stuff. You will, if you call up YouTube later and watch this show, those links will remain there. So you can find all the information, including the Python code and stuff like that, by going to those links. Okay. I'm going to turn it back over to Bob now.
Okay. So I guess I just go to Wikipedia for lots of stuff. And in fact, I think I even have these. Am I being shown now? Are people seeing my screen?
Yes, they see your screen, Bob.
Okay, so let's see. I guess I don't have the Wikipedia page for creating, but we could just go HR diagram, Wikipedia. There we go. So, I mean, this isn't explaining the math, but this is explaining in writing what I've said. And by the way, there's lots of history, and there's also some links here, which well, you know what? Here's another thing I would do. Code to make an HR diagram in Excel. How about that? There you go. And it's part of an APOD. Not quite sure what the APOD part of this is, but so I may have read some of these websites years ago, but it's just a matter of making a plot. If you got to be able to use a code to make plots. We've got two things. We've got flux or magnitude, absolute magnitude, relative magnitude, whatever you want to call it. You got to have those numbers, and you got to have some kind of measure of the color, the red minus the blue from the FITS files for each star is what I do, or blue minus red, I guess, whichever way. And since I don't really care about the units, that's all I do is I just get a table of two numbers, the brightness and the color, and then if you just get a table of these numbers, you load them into whatever plotting routine you like, whether it's Excel or MATLAB or Python or Julia, or maybe there's even apps that people have made in the astral world, which I haven't really looked for. But it's just a matter of plotting two things. So here's how to make an HR diagram in Excel. Please verify you are human. I'm not a robot. It's not going to show it to me. Here we go.
What's helping us here is we're assuming that all the stars are, the relative magnitude is the absolute magnitude.
Yeah.
We don't have to figure out differences.
That's right. And that's true for an open cluster that's all the same distance, and that's true for a globular cluster. If we'll go back to the picture, the plot I showed for all stars within 100 parsecs using Gaia data, there I needed to know the absolute magnitude, but the Gaia data tells me the absolute magnitude, so that was also very easy. But in that more general setting, yes, it's more complicated. You need to know the distance, the parallax, or somebody has to compute the absolute magnitude in some other fancy way. But if you're looking at a cluster of some sort, then you don't need to do that. You can use the relative magnitude because they're all the same distance away. And who cares if the actual numbers that you wrote on that vertical column weren't the absolute numbers? They're just the relative numbers. It doesn't really matter because you're still seeing the same structure.
Bob, isn't that the trick that Henrietta Leavitt used to figure out the variables are all the same distance apart because they're all in the Magellanic Cloud?
Yeah,
About the same distance apart
yeah,
from us. Yeah.
yeah. Yeah, and actually, I learned a little bit of the history when I was preparing for tonight. So Hertzsprung and Russell is what the HR diagrams are named after, but there was also a woman who was working at Harvard University. She has her degree in astronomy back in the late 1890s, I think, and she worked with Hertzsprung and Russell, and was actually a third person in figuring these things out. But because of the bad world we lived in 100 years ago, or I wasn't alive, and probably most of you weren't alive, but women weren't given the credit they deserve. But the Wikipedia page does explain that she also played a very key role in this idea of the stellar evolution being something very well defined and specific, and yeah.
Bob, why did you decide to do Hertz HR diagrams for your images? What are you looking for?
Well, the simple answer is because I'm a nerd, but okay, you don't want that answer. I like to try to measure distances to things. And so using the RR Lyrae, we're able to measure distances to other clusters because if we assume we know the distance to RR Lyrae. Now, of course, I haven't myself measured the distance to RR Lyrae, so it's cheating a little bit, but I like to do this ladder of this distance ladder type stuff. And in fact, I'm not doing it this year because I'm on sabbatical, but the previous 3 years, I was given the wonderful opportunity in the fall semester to teach a freshman seminar on sizing up the universe. How do we measure the size of things ourselves? And I start with the very simple question: how do I know the Earth is a sphere and not flat? And the students love discussing with me the Flat Earth Society. But the simple answer, of course, is look at a lunar eclipse. And I really believe, by the way, that 10,000, maybe 50,000, how far back do Homo sapiens go? How many thousands of years in the past were there Homo sapiens? Now, they didn't have books to read, they didn't have the internet, but their brains were probably pretty much just as smart as our brains. And they were living out in the desert somewhere, living under the stars at night. How many lunar eclipses? Of course, they probably didn't live to be 60, 70, 80 years old like we do these days, but they lived to be maybe 40 or 50 years old. And there's lunar eclipses, roughly speaking, every year. And how many it might not have been nighttime when they were living every year, but in the course of a lifetime, billions of people were living out there seeing a lunar eclipse multiple times in their life. I have to think, some of those lunar eclipses take place, let's say, just after sunset. So the moon's rising in the east, the sun just set in the west, and you see, and let's not talk about total lunar, let's talk about partial lunar eclipse. And you see part of the moon's cut off in a very weird way. And you've been living outdoors all your life. You've been seeing the moon basically every night. You live out in the desert where it's not cloudy. I really believe that millions, if not billions, of people had the thought, holy cow, maybe that's our shadow on the moon because the sun just set over there and this is rising over there. The reason they don't get credit for it is because they didn't publish it, or they didn't carve it into some stone on some wall somewhere, their idea. But I really believe that this is something people understood. Okay, that's a long, a long thing, but I really enjoy teaching this class because it starts with that conversation, and then we go, how do we know how big the Earth is? And we talk about how we measure that. And I've actually measured the size of the Earth from a picture I took of the sun setting on Lake Michigan. That's a whole nother story. Then we could look at the Earth's shadow. We know how big the moon is. We can figure out how far the sun is. And I went through this whole course. That's what excites me. How can we figure out the stuff that professional astronomers have figured out? How can we do that in the simplest possible way? Just using a telescope, maybe on your driveway. And the answer is you can basically do the whole thing. You can measure all the way out to other galaxies and how far away they are. You'll need to measure some spectrum. I bought a spectrograph, and so anyway, yeah. Enough said.
Okay, thank you, Bob. That was very informative and challenging, I think, for a lot of us to, realize that taking the data that we've already got, if we can figure out how to get a program to read an image and tell us how bright the stars are in there and what their colors are, and we can get a program that will plot all that data for us, we can actually make HR diagrams like you did tonight and learn a little bit from it. Thank you very much.
And I'll post the MATLAB and the Python codes for those of you who have some comfort with those languages. I unfortunately don't have it in other languages, but I can post both of those.
Okay, thank you.
I would like to, Bob, I would like to invite you again, if you would, to come back to Astro Imaging Channel and talk about your star shade.
Oh, okay. I could do that.
Bob worked on, would you like to tell us a little brief description of what that was?
Sure. I started working on this
Bob,
project.
incidentally, you're still screen sharing. You can stop your sharing and go back to we can see you.
Okay. Hello. Wait a minute. You see me?
There you go. Hi.
I have to go back to you guys. Oh, there you are.
Yeah.
Yeah. So I started working on this project about 2001, 2002. So just after my amateur astronomy interest got rekindled in the year 2000, I started working on a research project with a person who became one of my best friends in mechanical and aerospace engineering, and another person, his name is Jeremy Kasdan, and another person who became the chair of the astrophysics department at Princeton. His name is David Spergel. The three of us wrote many, many papers to help NASA design and eventually build a space telescope that would be able to take direct images of Earth-like planets around sun-like stars. That hasn't been done yet. We have taken some pictures of planets around stars, direct pictures, only a few, but we haven't taken pictures of Earth-like planets around sun-like stars because they'd have to be pretty close. And if you could look back at our solar system and see the Earth going around our sun, the sun is 10 billion times brighter than the Earth in a picture. 10 billion to 1 is a huge contrast. I was complaining about just, a few thousand in between the bright stars and the dim stars in an HR diagram. We're talking about 10 to the 10, 10 billion. And so NASA was going to launch a space telescope to do this called Terrestrial Planet Finder Space Telescope. And they were going to launch this in the year 2014. Sadly, it didn't happen. Sadly, most of you, probably maybe all of you, never even heard about the Terrestrial Planet Finder Space Telescope, which was abbreviated TPF, because sadly, TPF was canceled in 2008 when there was budget crisis. But the NASA project was to build a telescope that could do this high contrast imaging. And there's two competing concepts of how to do this. And one of them is to use a star shade. And that is, if you're looking at a light, like I'm looking at right now, the light that's shining in this room here, and I put my thumb up, I can block the light, and now I can see things around it. And that's the idea of a star shade. Launch a space telescope and another spaceship, which has just a big screen, a big open.
Well, don't reveal too much. I want you to come back and tell us the whole thing.
Okay, so it's about that. It's about designing this star shade. Enough
Okay.
said?
Thank you very much for your presentation tonight, Bob. And I think we've got all the questions over there, Eric. And so, Eric,
Yeah, I'm sorry,
Yeah,
just had to. switch my
I
mic.
think,
We're all
yeah.
set.
okay, next week, Tim Conley is going to come over, and I don't know, your version of cold and my version of cold are two different things, because I'm living in Southern California, and many of you are living in a lot of places that have much colder weather than I have to live with. But Tim's going to be telling us about how to image in cold weather, bad weather, and he's from upstate New York and kind of over there in that snow belt region, just east, I think, of the lakes. So he's going to have a lot to tell us. Hope to see you back next week. And Toga, I think you could take us out. Say good night, everybody.
Good night, everybody.
Thank you.
Good
Okay.
night.
Good night.